Hello everyone, and welcome to the last section of Chapter 7, which is using exponential and logarithmic functions. So really, we're not learning anything new this section. It's more of a matter of using everything we know about exponentials and logarithms to solve problems, make predictions, figure out when something might happen, figure out how long ago something might have occurred. So really the application kind of aspect of all this stuff beyond the money. One little thing that they added is just because we have the exponential growth and decay stuff. If it is continuous, we have AE to the KT, where K is a constant, which usually is what we're solving for. And then remember, if we want to get K out of that exponent, once we isolate that E to the KT portion, we can take the natural log of both sides, and that'll take the K right out of the exponent and make it easier to work with. So, a lot of these problems are going to be very situational. You're going to use versions of this sort of formula, but because every situation is different, like our K value is going to be different, and we'll know if it's a growth or decay based just off of whether or not that exponent's positive or negative. So, let's take a look. So half-life, we have the half-life of sodium-22 is 2.6 years. Determine the value of K in the equation of the decay for sodium-22. So half-life, you've hopefully seen in science class. Half-life just tells us after how long does half of my substance decay away. So it tells me exactly at which point, after however many years, minutes, hours, whatever it is, we only have half of what we originally started with. They use this a lot with like carbon dating. They can determine how old something is based on the amount of carbon and its half-life. So, I don't exactly know, how much we're starting with, but really it doesn't matter because I'm talking about the half-life, so I'm looking at half of my starting amount compared to my initial amount. And then E to the, I know it's a decay, so negative 2.6 times my K. Now I want to figure out what K is, so I'm going to divide both sides by A to get the E all by itself, and the A's drop out nicely for us. So, in order to get that K out of the exponent, in order to actually work with it, I've got to take the natural log of both sides. So I've got natural log of 0.5 equals, remember natural log of E simplifies to 1, so I will be left with that exponent which dropped out in front. I could divide both sides by that negative 2.6. And at this point, pull out my trusty calculator to figure out what I have. So natural log of 0.5 divided by negative 2.6. Notice how I close my parenthesis. And I have a K value of about 0.2666, we'll say. So my equation of decay will then be just plugging in that K value. So I've got whatever my amount is, we can call it Y, we can call it f of x, either or, equals whatever amount I started with, E to the negative 0.2666, and then since I want the overall equation of decay, whatever amount of time I'm looking for will be T. If I wanted the half-life equation, I would plug in that 2.6. So, very similarly, if a geologist was looking at a meteorite that only had 10% of the sodium-22 as it probably contained when it reached the surface, how long did the meteorite reach the surface of the Earth? Well, we can use that formula we just found to figure it out. If I have 10% as much as now as I did whenever it landed, I've got 0.1 of my starting amount equals my starting amount and then E to that equation that we just found. Now I've got to isolate my e, so very nicely I just get rid of the a on both sides. I want to get that t out of my exponent, so I'm going to take the natural log, since I do have a base of e. That brings this out of the exponent, so my natural log of 1.1 is negative 0.2666t. I'll divide both sides by negative 0.2666, and I'll do that on my calculator. So the natural log of 0.1 divided by negative 0.2666, and I get about 8.64, or about 8.6 years ago. So a little bit more than 8.5 years ago. Because it makes sense that population doesn't just sporadically gain people at the end of, say, each year or each quarter, it kind of just continuously happens. Population growth is a good way that this continuous growth, or potentially decay, can be modeled. So, if we're looking at 2007, the population of China was 1.32 billion. In 2000, it was 1.26 billion. Determine the value of k, which is China's relative rate of growth. So, I'll set up my equation. I know my quote-unquote present amount, or the amount I have after a certain amount of time, is 1.32 billion. They're both in billion, so there's no issue just leaving it as 1.32. We know in the context that it is billion. I started out with 1.26. Don't forget your e. We don't know our k, that's what we're looking for. Our time, however, is 7, because it's from 2000 to 2007, that is 7 years. We know that it is going to be a positive k value simply because it's talking about a growth. We went from 1.26 to 1.32 instead of the other way around. So we can isolate our e by dividing both sides by 1.26. .32 divided by 1.26. I'll actually, for rounding purposes, leave that the way it is for now, even though it is in my calculator for later use. As you may have guessed, we are indeed going to take the natural log of both sides. So I'm going to take the natural log of that number I just found. So natural log, I can pull up my answer by hitting second negative. Again, I'm going to leave that in my calculator for purposes of not having too much rounding. And then since this will be out in front, and I'll just have k times 7. If I want k all by itself, I'll just take that answer I just got and divide by 7. So, I have 0.0066457.165. We'll make it 0.0066 for short. Since that's a decimal, if we want to kind of make sense of that, that's going to be about 0.66%, if we wanted to think about it that way. But that is the k that we would plug into our equation if we were going to be solving for anything else. For example, if in 2007 the population was 1.32 and in 2000 it was 1.26, we can use that equation, that k that we just found, to figure out when we might reach 1.5 billion. So I'll utilize my k value from above. I want to get to, or I'm looking to see when I might reach 1.5 billion. I started out with 1.26. I've got E. My K value I just found was 0.0066. And I'm not sure when this will happen. My T is my variable I'm looking for. I'll divide both sides by 1.26 to get my E value all by itself. We will take the natural log of both sides. Remember, our exponent comes out in front, so we are left with only our exponent, since the natural log of E is just 1. And then we'll divide both sides by 0.0066. So we pull out our calculator. Natural log of 1.5 divided by 1.26. That gives it an answer. And then I'm taking that and dividing by 0.0066. I get a T value of 26.4 approximately. So that tells me that my population will reach 1.5 billion probably somewhere in the year of 2026, since that's the amount of years since 2000. So 2000 plus 26 is 2026. All the problems in this section are going to be very situational like this, looking for a particular variable within our equation based off the given information. So that's about it for 7.8. I will see you in class.